So let's look at our data set. All right. I'm saying in this data set, IDS data set, now we have got only 4 variables that we have. And we want to standardize the data so that they are in the same magnitude. So use the scale function to scale the data, and then you run it. Yeah, there are a lot of people that were joining, so I decided to. So now we are saying let's scale our data so that it's in the same magnitude. So I run the scale function with my data. So I give my data an object name that is now clustering. So let's look at the data that has been what scaled. So if you look at the data that has been scaled, you see that the data is almost approximately close to each other. All right. We may use another transformation. You may use logarithm transformation, but if you've got zeros for logarithm transformation, it wouldn't work because it's undefined when it's a 0. Now, we remember I talked about non-hierarchical clustering. We talked about hierarchical clustering. We talked about fuzzy. We talked about model-based clustering. So now let's look at examples of non-hierarchical clustering. One of them is the k-means. The other one is the what you call the partitioning around the medians, right? So you're saying the k-means algorithm is an iterative algorithm that tries to partition the data set into k. Oh, just excuse me. Yeah, there are a lot of people that are joining. Yeah, you should join by on time so that we are active at once. So now we have seen that we have we have standardized the data, which is that format. So k-means clustering, we're saying if k-means algorithm is an iterative algorithm that tries to partition the data sets into k predefined, distinct, non-overlapping subgroups, where each data point belongs to only one group. So we have got what you call predefined, non-overlapping what subgroup. We call them what clusters, where each data point belongs to only one particular group. So there are steps that you need to do. Suppose you're carrying out k-means clustering, right? The first step that you need to do is to determine the optimum number of what? Of clusters. So I'm sure you now know how you can get the help function from R. This is the function for determining the optimum number of of clusters. So if you take that function and put a question mark, and then you put that function, and then you find the help, it explains in detail on what that function does for you, right? On where the plot usually comes from. So read about that function and you try to understand it more detailed than what I've done. So here I've just placed some commands for you to a few commands for you to understand the basic functions about clustering. So I've said k-means is equals to this function, right? And then I call my data set, which is clustering, and we have got what k-means is the method, right? You have WSS, and then you are now saying geo vline. Now we are putting the lines, right? So the line x-intercept is equals to 2. This is what we call it's guesswork for initially, probably C after this guesswork. And then the line type is equals to 2, which means I need line type 2, which is probably a line. Right? If I run this, and then I print the function. So now there is what is called the total within sum of squares and the number of what of clusters. Number of clusters, they are stretching from 1 to 10. Then we have got the total within sum of squares, which is 0 to what to 600. So what happens? This is what we call the elbow method. Elbow method, where you look at your graph and you choose where there's a particular point which gives you the number of clusters, where the line in blue are usually bands or elbows, right? So you see it either elbows at what, at 2, or elbows at what, at 3, elbows at 4, at 5, at 6. But now you need to pick an optimal point. So if I'm to argue, I would say it elbows at 2 or 3, because if you're looking at the change from 3 to 4, it's not significant, the change, right? Even look at 4 to 5, the change is not significant, 5 to 6. So the change that was significant is from 1 to what, to 2, and even from 2 to what, to 3. So I may decide to say, okay, let my number of clusters be what, be called k equal to what, to 2, or k equal to what, to 3. So if you decide to say, okay, I think my optimal number of clusters is k equals what, k equal to 3, it's you, and then you need to argue based on the variation between the previous and the after cluster. So if you're going to look at, probably you put it 3, yes, I think 3 can be suggested as the number of clusters. There is no final answer, but you need to have a justification. So you need to be able to argue based on the result to say, okay, I think k is equal to 2 is the optimum number of clusters that you can have for this particular data using k-means. But I think you may argue and say, probably 2, it might be a better what cluster. So look at my comment here. I said the location of the bending is in the plot, generally considered as an indicator of the appropriate number of what clusters to be considered. The plot above represents the variance within clusters. It decreases as k increases, but it can be seen a band at elbow is equals k equals to 2, right? This band indicates that the additional clusters beyond that have a little what of value, right? Someone may decide to use what 3. Okay, for analysis sake or for the lecture sake, let's check k is equals what to 3, and then probably I'll change k and say it's 3. Then, so here now we need to assign each observation to a particular cluster, right? So you realize here I've picked again the what, this is e-cluster function, right? And then here I'm calling up on the data, right? And then this is k-means the method, and then k is equals what to 3 now. So if you run that function and then I print it, right, it will assign each and every observation. Remember, we've got 150 observation, right? So you realize observation 1 to observation number 50, then cluster what? Cluster 1, right? Then now you realize the next observations from 3, they are in cluster what? 3. So you're trying to assign each and every what observation into what? Into a particular cluster. Since you've selected what? 3 clusters, right? They assign each and every observation into what? Into a particular cluster. So play around with those functions, you get more impression about that. So the second step, we are saying assigning each observation to a particular cluster. Then number 6, so line 64, we are saying let's visualize what we have obtained above that we have assigned each observation to 3 clusters, right? So you run this, right? Then after running that, you have to look at the visualization. We see the graph that we have here. It gives us 3 clusters. But I'm sure in your notes I talked about what a good cluster means. Even just before we started here on the above, I explained what's a cluster. It's a distinct, non-overlapping subgroups. So in this situation, you see there's an overlapping of certain 2 clusters there, right? The overlapping of those 2 clusters, right? It means that the number of clusters that you might have selected are not good enough for us to have those 3 clusters, because we have to reduce the number of clusters catering for that. So suppose we choose k is equals to 2, right? Yeah, I'm changing now from the optimal number of clusters, right? It's 2, we've picked 2, right? Let's see what's the visualization, all right? And let's calculate again. Let's assign each observation to a particular cluster. Then we've assigned that, right? You see you've got only 2 clusters now, right? Because we have assigned to 2 clusters. So let's look at the plot or the visualization. Does it give us the same what? Results? You see now, this is a better clustering technique, but somehow you need to argue based on the results, right? We have selected what? 2 clusters, and those 2 clusters now they are confined, they're coming up, there is non-overlapping. So this is a descriptive analysis where you need to argue based on your results. 3 clusters, they might be suitable, they might not be suitable, but at the end of clustering analysis, doing all the approaches, you'll be able to what? To argue and have a final decision on what's the appropriate number of clusters for a particular data. So you're going to implement different methods. Right now we've applied the k-means, right? So based on the k-means, we are saying the visualization of the k-means seems good in the sense there is none overlapping. So if you choose k is equals to 2, there is none overlapping. When you choose k is equals to 3, there is what is overlapping. So we would be able to argue on the basis of that. I saw somebody raising their hand. Who is that? Any question on k-means clustering?
See, I just want to ask you, parents assigning each observation to a particular class, the parametric graph is supposed to false in the instat is equal to 50. What does that mean?
Yeah, that's why I said I gave you these commands. Now you guys are able to learn these things, right? If I just tell you n is equals to 50, it's not enough for you. You can use question mark, right? E cluster, all right? Go and read. It's for you to read more. I'm not. I shouldn't tell you. There are a lot of functions that you can use within that particular data set. So go and understand what e-cluster does, so that you'll be knowing whenever we use e-cluster, you know what are we doing. If you use question mark
Okay.
e-cluster, go and read everything like this. I'm sure you can see on the right hand side, it explains about e-cluster in detail than what I would have said. So there are certain functions that I didn't include in that have been included here. So if you read more, you get more than what I have assigned you.
Thank you.
Yes. So it will be good for you if you do it practical, and then I've created commands for you. Uh, that's easy. If you've got a starting point, and then you're building from there. Any other question on k-means? Right. Let's look at now what is called the PAM, which stands for partitioning around the medians. That's another method for clustering, which falls under what you call non-hierarchical clustering. So the algorithm intends, sorry, I think there was a grammatical error, intends to find a sequence of objects called midjoins that are centrally located in a cluster. Right. So we're mainly looking at observations that are centrally located in what? In clusters. That's the PALM method. So the same approach again, we would have to determine the optimal number of clusters. So the only way to determine the optimal number of clusters, in this case, we use what is called the average silhouette method. Right. So the average silhouette method measures the quality of what? Of clustering. A high average cluster, an high average silhouette width indicates a good what? A good clustering or a good cluster. All right. So you see, I repeat the same this function. I think I did use it above, right? For determining the optimal number of clusters. If you come and check on k-means, this is the function. So you can come up with a better visualization than what I have done, which explains better what our results. Right. So this is the PALM. So this is our data set clustering. Right. This is our particular method that we're looking at. Right. This is the method of what? Of determining the optimal number of what? Of clusters. So if you run this and then you print it, sorry, I deleted it. You print it, it will give you what? 2 is the optimum number of clusters, right? Because I said a high average silhouette width indicates a what? A good cluster. So the PALM is suggesting what? 2 is the number of what? Of clusters, right? Now, we now want to assign each observation to what? To a particular cluster, so that you are able to come up with what? With the visualization. Because after assigning each observation to a particular cluster, you'll be able to what? To come up with what? With the visualization, right? So if you run this function, right, since it has picked the 2 clusters, this is the 2 clusters that we've come up with. Let's look at the visualization of those. Sorry, we are assigning the observation to each particular cluster, right? So we've assigned observations to each particular cluster. Then now we come up with what? With the plot. I'm sure you know this function is for what? You would have to read about these palette functions for coloring. You may realize that your data sets requires more than 2 clusters. So you need to find different types of what? Of coloring. So this is, let's look at the visualization part. Yes, I think it gives a warning, but it gives us the plot, considers increasing maximum overlaps. So too many overlaps. I think probably it might be the issue of the number of clusters that you have selected. So you try to alter and see whether what comes out of the number of clusters. So you see, even the PALM, it also suggests what? 2 number of what? Of clusters, and there's none overlapping there. So the visualization of the PALM clustering seems good in the sense that there is what? There's none overlapping. This is a hint that I'm giving you. You shouldn't just expect to get maximum marks based on these interpretations. You have to, this is an assignment. Google, the more you Google, the more you learn. Right? So get on Google as a group for the assignment, right? Start finding more, just find a way to impress me. Don't just do what you have done on this or whatever I've given you. You can do better than that. You've got that skill to do the better. I want you to be better than me, but I've introduced you to these components, and just go ahead and be better. So any question on PALM, which is the partitioning around the midjoins? So next, let's move on to hierarchical method. Right. The hierarchical method is it's a clustering technique that requires you to compute the distance first. Right. You compute the distance of the data set that you have. I think here it's a mistake. You should be clustering. Right. So you see that's advantage of you coming for a lecture. You can see the mistake that I would have done on typing. So that's clustering. So the method that I have decided to use, which is the most widely used methods in terms of computing my distances in machine learning, is the Euclidean distance measure. So I have just calculated the distance for our data. All right. I think there was an issue of spelling error there. So if you print, let's print the distance and see what's the distance of our data, right? Every time you run a command and visualize what's inside, right? So it's a big matrix here that we have, right? So it gives us the first observations, right? So it's a distance between the objects, right? So I think you're talking about 150 observations. So I'm sure it'll be 150 by what? 150, the dimension of the distances. So now, when I'm dealing with the hierarchical clustering technique, we usually use what is called the dendrograms, right? We use what? The dendrograms for visualization of the what? Of the hierarchical clustering. So you're saying in hierarchical clustering, you categorize objects into a hierarchical similar to tree-like diagram, which is called a what? A dendrogram. I'm sure you've seen a tree. We've got some branches, right? Those branches, they become dendrograms, right? So you're saying the hierarchical similar to in terms of the what? Tree diagram, which is called what? A dendrogram. The distance of split or meshed code is height on the y-axis and the dendrogram below. So the distance is represented by on the vertical axis, which is the y-axis, called the height of the dendrogram. So in hierarchical clustering, we can since we have used the k-means and palm, we can now suggest the number of clusters that you can probably fit for our what to call this, our particular number of what. I think there was a mistake that I did here. What mistake did I do? Because, okay, it's okay. Let me see. Okay, this command wasn't supposed to be here. Right, since we have used the k-means and palm, right, we probably have a hint on the number of clusters that you can select, right? I think we've got okay, I see what I did.
Hello there.
Or 40 minutes, it's Zakwana. You can save the recording and then we can restart again.
Okay, all right.